Hello everyone, welcome back to my channel. Today I'm going to discuss a very important topic in organic chemistry, which is molecular rearrangement. I would like to begin with the basics of this chapter. First, let's see what a rearrangement reaction is. It is a type of reaction undergone by the organic compounds. I've given a detailed explanation here. A rearrangement reaction is a broad class of organic reactions where the carbon skeleton of the molecule is rearranged to give a structural isomer of the original molecule. From this definition, we see that rearrangement reaction is not just one reaction, but it is a broad class of many organic reactions. And we say carbon skeleton because here we are only talking about organic compounds. And organic compounds have a general carbon skeleton as their framework, in which many other elements and atoms are accommodated. So this is the basics that you should be knowing. Now, what exactly happens during a rearrangement? I told you that there are some atoms or groups incorporated in the carbon skeleton. Those atoms or groups will undergo a reshuffling. That is, they will try to change places during this reaction. When they do this, they give you a structural isomer. A structural isomer of the original substance or the initial parent compound that you have taken is obtained. Now, what is an isomer? We all know that an isomer is a compound that has identical formula but will have a structure different from that of the substrate or the reactant compound. So, a structural isomer, that is a compound with the same molecular formula as the substrate but with a different structure will be produced due to the rearrangement reaction. Here I have written down what isomers are. These are nothing but molecules or compounds with identical formula, but they'll have a distinct arrangement. That is, the arrangement of atoms in space will be different. For example, if you take two molecules which are supposed to be isomers, the first molecule will have one structure and the second molecule will have a structure just the opposite or different from the first structure. But these two are isomers because they'll have the same molecular formula. That is, same number of carbon atoms, same number of hydrogen atoms, same number of oxygen atoms, and other atoms present. So those are only called as isomers, and at the end of a rearrangement reaction we get an isomer of the original compound that you have taken. Now let's look at the two types of rearrangement reactions. First one is intramolecular rearrangement and the second one is intermolecular rearrangement. The first type is one where the migrating groups, or I already told you that the atoms are changing their place. So those are the migrating groups. These migrating groups will not detach themselves from the reacting organic compound or the substrate that you are taking. But on the other hand, in the intermolecular rearrangement, the migrating groups will detach completely and then they reattach later on. So these are the different types. To understand these two types of rearrangements, you can take examples from your own life. When you were in school or you were in college, they used to say intercollegiate competitions, inter-school competitions, which is competitions held between different schools or different colleges. So that means it is outside. You are going out to take part in different competitions. The same happens in this case also. The migrating groups will go out, that is, they will detach themselves from the substrate and they'll go out, then they recombine. Only the migrating groups will recombine, leaving the rest of the compound behind. That is the intermolecular rearrangement. This type, intramolecular rearrangement, can also be cited with the same example. Intra-departmental competitions, that's what they say in colleges. It means that the competition is happening between different departments like physics, maths, computer science, so on, within the same college. Thus, you come to a conclusion that it is happening inside. You're not going to go out to participate in a competition. Thus, the migrating groups here will not go out. They won't detach themselves from the compound and will take part in the reaction the same way. Today, I'm going to discuss three rearrangement reactions, of which Pinacol Pinacolone rearrangement is the first one. Here Pinacol is the reactant and Pinacolone is the product. Let's look at the summary. Pinacol first reacts with hot dilute sulfuric acid and it undergoes rearrangement and dehydration to give Pinacolone, which is a monoketone. This is the basic summary of what will happen in this rearrangement reaction. Let's look at the terms. The terms Pinacol and Pinacolone are not very familiar. So I will tell you how to remember these compounds and their molecular formulas. Basically, Pinacol has a molecular formula containing a vinyl group, which is CH double bond CH2. It is nothing but an ethylene molecule with one hydrogen short. This is a vinyl group. To this vinyl group is attached two OH groups, that is alcohols. You know that when there are two hydroxy groups present, you call that as a diol. Thus, Pinacol is an organic compound with a vinyl group attached to two hydroxy groups. That is Pinacol. Now I'll tell you how to write the molecular formula. Now we are going to look at the molecular formula for a Pinacol. I have written the basic structure or the basic vinyl group. Here you have two carbon atoms which is in the position 2 and 3. Now I'm going to replace all the hydrogens with methyl group, and obviously we know that two hydroxy groups have to be attached to make it a Pinacol. We know that carbon can form 4 bonds. It has already formed one bond with the neighboring carbon atom which is represented here. The other hydrogen I am replacing with methyl group, which is this. This side another bond is formed with methyl group and it is attached to an hydroxy group. This carbon atom, again there are two hydrogen atoms attached. I am replacing both of these hydrogen atoms with methyl groups and one hydroxy group is attached. Now we have a molecule of Pinacol. I am going to number the carbon atoms and name it. We see that these methyl groups or the carbon atoms of the methyl group will also account to the parent carbon chain. So I am numbering it from this side. 1, 2, 3 and 4. There are 4 carbon atoms showing us that the parent is a butane because it's all single bonds. Now I am going to name this compound. By looking at the compound, you can see that in the second and third position, there are 2 methyl groups and 2 hydroxy groups attached. So based on this, let's name this molecule. I'm writing 2,3 dimethyl because there are 2 methyl groups and the parent carbon chain is butane because there are 4 carbon atoms. So butane. And again in second and third position there are hydroxy groups. Again I'm going to write 2,3 diol. This is called as a tertiary glycol. Glycol because there are 2 hydroxy groups attached, and tertiary because both the carbon atoms are tertiary carbon atoms. That is, all the hydrogen atoms are being replaced by other groups. Thus it's called as a tertiary glycol, and this is the main reactant for our rearrangement reaction, which is Pinacol. Let's look into the general reaction. This is the general reaction for Pinacol Pinacolone rearrangement. Here you see that Pinacol is the reactant and Pinacolone is the product. We have sulfuric acid as the catalyst. Since it's taking place in the presence of sulfuric acid, we see that this reaction is happening in an acidic medium. So you will have a free proton that is present. Let's look at the mechanism for this reaction. In the mechanism, the first step is protonation. Protonation is nothing but the addition of a proton. Now I am writing the Pinacol or the reactant which has the 2 hydroxy groups attached to it. This is the molecule of Pinacol. Since I told you that there is a free proton that is present in an acidic medium, it will try to combine with the highly electronegative atom oxygen. Oxygen has two lone pairs of electrons and proton doesn't have any electron. It is deficient of electrons. So the proton, which is electron deficient as I already said, will have a high tendency to form a bond with the electronegative oxygen atom. Oxygen atom, we know that it is electronegative and also is rich in electrons. So it will share its electrons with proton to form a bond, which is why it is called as protonation, because you are going to add a proton to this compound. So the first product that you will get is CH3CC, CH3, CCH3, CH3, OH. Here you see that oxygen is forming a bond with hydrogen. That is, it is going to share its pair of electrons. Thus, it will attain a positive charge plus. So, it will be OH2 plus or H2O plus. Thus, this is the first product that you get by protonation. The next first product that is formed out of protonation is highly unstable because oxygen, a part of this molecule, is carrying a positive charge. It can be any charge for that matter. This will make this molecule highly unstable. So this molecule will somehow try to eliminate the part that is carrying a charge in order to stabilize. That is what is going to happen in the second step. It's going to eliminate water. So this step is called as dehydration. I'm writing step number 2 minus H2O on top of the arrow indicating dehydration. So this part is going to be removed. We know that oxygen is electronegative. So when it is leaving, and also it's positively charged. So when it is leaving, it will take the electrons that is forming this bond. The electrons forming carbon-oxygen bond will be taken away by oxygen. Thus, it will leave a positive charge on carbon, making it a carbocation. So the second product that you will get is a carbocation. CH3C, CCH3, OH. This part hasn't changed. Now this carbon will have a positive charge. And now you have CH3 and CH3 plus H2O. That is, the water molecule has been eliminated. So the second product formed is a carbocation. We discussed that earlier. Now what kind of a change is this carbocation going to undergo? That we will see in the third step. The result of dehydration, we saw that a carbocation is being formed, and this is the second product that we get. Now this product, all of these products are only intermediates. The final product will be the desired product. I will make a mention of what the final product is. So you see that this second product, being carbocation, is also unstable because it carries a positive charge. That is, carbon in the chain is carrying a positive charge. So it will undergo a reaction in order to nullify this charge. Since it's a rearrangement reaction, you see that one of the methyl groups attached to the other carbon atom, neighboring carbon atom, will try to shift to this place in order to nullify this positive charge. Due to the shifting of methyl group, the positive charge on carbon number 3 will get nullified. So carbon will no longer be the carbocation. But on the other hand, carbon number 2 is the one that initially had this methyl group, and it is donating it to the other carbon atom, neighboring carbon atom. So now in this step, carbon number 2 will obtain or will acquire a positive charge. Thus, in step 3 or the product 3 will have a carbocation, which is carbon number 2. This carbocation that is formed is also unstable because of the positive charge, and we know that this oxygen atom also has two lone pairs of electrons. Now, how will this charge be nullified? It will be nullified by the donation of electrons by oxygen. It will give this lone pair to the carbon atom, carbon number 2, which is deficient, having a positive charge. Thus, it will get nullified and it will give you a positive charge on oxygen, because oxygen is the one that is losing the electrons in this case. Carbon number 2 will not have any charge because it is nullified, and oxygen has donated a pair of electrons towards carbon number 2. So it will form a double bond, because a pair of electrons can lead to the formation of one bond. There's already one bond, so this pair will give you another bond. Thereby you will have carbon double bond OH, and this oxygen will have a positive charge. I hope you can see. So this oxygen will have a positive charge and hydrogen is attached to it. Now carbon number 3 as usual will not be changed. It will be attached to 3 methyl groups. This is the fourth product. The fourth product is one which has an oxygen atom carrying a positive charge. So here, in order to nullify this positive charge, hydrogen will be removed. That is, proton, it will be removed in the form of proton, H plus. So I am writing minus H plus because proton or hydrogen is highly electropositive. So when it leaves a compound or a molecule, it will not take any electrons with it. Either it will only give the electrons that it initially donated to form a bond. Thereby when it is going out or when it is leaving the molecule, it will leave as H plus, being highly electropositive or electron deficient. So the electron that is left by hydrogen will be taken up by oxygen to nullify this positive charge. Therefore, the product formed by deprotonation, that is removal of proton, is CH3C, C double bond O, because only double bond O is present as hydrogen has been eliminated. And then the third carbon atom will not have any change. It will be bonded to 3 methyl groups. This is your final product, which is 3,3 dimethyl 2-butanone. 3,3 dimethyl because to carbon number 3 there are 2 methyl groups attached. Not this because it's in the chain. This is not a methyl group. This is a carbon atom in the parent chain. So this is not considered as a separate group. Only these two are substituent methyl groups. So to carbon number 3 we have 2 methyl groups. So I am writing 3,3 dimethyl. 2 methyl is represented as dimethyl and 2-butanone because one is written when you have a ketone. When you have a ketonic group present in the molecule, you represent it as one. That is, you give a suffix ONE. Here you have the ketone in the second position. This carbon is the second carbon, right? So 2-butanone. Methane, ethane, propane, butane. Butane is the parent carbon or the trivial name from which you see that it's a ketonic group that is attached in the second position. So you write butanone. 3 dimethyl 2-butanone is the final product that you get from a pinacol. I'll show you the main reaction that I already wrote. So this was the first reaction that I wrote. Here we saw that pinacol will give you pinaclone by reacting with sulfuric acid, and we saw how it works. First it is getting protonated, next it's getting dehydrated, and finally it is getting deprotonated to give you 3,3-dimethyl 2-butanone, which is nothing but pinaclone. So this is the Pinacol Pinacolone rearrangement. I hope now we are going to discuss another rearrangement reaction called Benzil Benzilic acid rearrangement. This is a reaction that can only be undergone by an alpha diketone, which is also called as a benzil. This is a base catalyzed reaction. Why? Because in Pinacol Pinacolone rearrangement that we discussed previously, it took place in an acidic medium, that is sulfuric acid. Since this is a base catalyzed reaction unlike the previous one, it will take place in the presence of a base, KOH, potassium hydroxide. Another important step that should be followed here is, in this rearrangement, after the base catalyzed reaction, the reactant benzil will undergo acidification, that is protonation. When it's called an acidification because there will be a free proton that is present in the medium. So it will undergo acidification to give us the desired product, which is benzoic acid. Now let's look at the general reaction and then we will look at the mechanism. This is the general reaction for this particular rearrangement reaction. Here you see that benzil will undergo a reaction in the presence of KOH and H+. H+ because I already told you benzil will also undergo acidification even though it is happening in the presence of a base. So it is written as H+ at the bottom of the arrow because both of this will be present in the reaction medium. And benzil, as I told you, will undergo these reactions to give you benzoic acid. Now I'll tell you how to remember what benzil is. Benzil is an alpha diketone. Alpha carbon atom is the carbon atom that is attached directly to a functional group. Here you have two carbon atoms, both of which are attached on either sides with a functional group. Phenyl group, C6H5 is a phenyl group. So this carbon is attached to a phenyl group and this carbon is also attached to a phenyl group. Therefore, these two are considered as alpha carbon atoms. I'm writing alpha and alpha dash, or it can both be alpha. Just to make a difference, I'm writing alpha, alpha dash, but both are alpha carbon atoms. And both of which are ketonic carbons, that is C double bond O. Therefore, you write alpha diketone. Since there are two ketonic groups present and both are in alpha position, I'm writing alpha diketone. Only an alpha diketone, which is also called as a benzil, can undergo this reaction. And benzoic acid, you know that there is a COOH group and one of the carbon atoms will be attached to an OH group. So this is the reaction, general reaction. Now I will give you the mechanism. The first step in this reaction is nucleophile addition reaction. A nucleophile is represented as Nu- because it is an electron-rich ion and it has a natural tendency to go attach itself to a highly electropositive or electron deficient ion like a carbocation or any other ion that has a positive charge. So this information will be helpful for you to remember and understand the first step. For the first step to happen, you need a nucleophile. Now I'm going to generate nucleophile from KOH. KOH is the base catalyst that we are making use of in this reaction. So the required nucleophile will come from KOH. KOH will split up as K plus and OH minus. This is a reversible reaction because these two are ions and they are oppositely charged. So they usually have a very good attraction between them. So they can recombine to give you KOH. But for now we need the nucleophile, which is OH minus. This is also the nucleophile because it is highly electron rich. This is the nucleophile that is required for this reaction. Now I'll show you how this nucleophile attacks our reactant. Now I'm writing the reactant, which is alpha diketone. C6H5, C double bond O, C double bond O, C6H5. For the nucleophile to attack, I need a positive center or I need a center that is electron deficient for the attack to be made possible. So this carbon atom has, either of these carbon atoms should be positive because they both are attached to oxygen atoms and they can be made positive by giving away the electrons to oxygen, which is electronegative in nature. So I'm choosing this carbon atom. You can even choose this carbon atom. This carbon is giving the electrons to oxygen, or you can also put it in other words that oxygen is abstracting the electron that it is sharing to form a bond with carbon. So when this process happens, carbon, which is forming 4 bonds initially, will only be having 3 bonds after this shift. So it will be carrying a positive charge. I'm going to write it as C6H5, C double bond O. There's no change in this part of the molecule. But here, when you write carbon, you will write C plus and O minus, because oxygen is taking the electrons back, so it will get a negative charge, O minus and C6H5. Now we have the desired carbocation. This is the first product. Now we will see how the nucleophile OH minus is attacking the carbocation. This is a reversible reaction because the opposite of this reaction can also happen. Now I am going to write the nucleophile on top of the double-headed arrow mark. Double-headed because it is a reversible reaction. OH minus electron rich. So it will go and attack carbon, which is positively charged. When it attacks carbon, it will give its electrons to form a bond with it, thereby neutralizing its charge and also neutralizing the carbon's charge. So it will be C6H5, C double bond O. CO minus will remain as such, and to this carbon OH is attached and the other phenyl group. This is the product that you get due to the nucleophiles attack, and this is the first product. Now this first product is highly unstable because of the negative charge on oxygen. So the other step will be the shifting of this negative charge. We see that there are two types of shiftings that are happening. The first shift is the negative charge is shifted towards carbon to form a double bond. This carbon atom is shifting this double bond towards oxygen to make it O minus. So the intermediate product that you get is C6H5, C O minus, C double bond O, because the double bond is formed because of the shifting of the negative charge and it is attached to OH, and then C6H5. This is the intermediate product. I am naming it as 1, that is Roman number 1. This is also again unstable because the whole point of this reaction is to keep stabilizing each and every molecule that progressively becomes unstable in every single step. So I'm going to stabilize this product, but the thing is, when you have to stabilize this negative charge, I have to shift the phenyl group. Like we saw in the previous rearrangement reaction where I was shifting the methyl group from one carbon atom to the other carbon atom, right? If you remember, you'll be able to understand this. So here I'm going to shift phenylic group or the phenyl group towards this carbon atom just to make this carbon atom or this oxygen stable. This shift is called as 1,2 phenyl shift. One thing that you have noticed here is there are 5 bonds for carbon atom. This is definitely not possible. The shift of phenyl group has to happen because carbon is already having 4 bonds. It cannot have another extra bond. So phenyl has to shift. This shift of phenyl group towards this carbon atom happens as soon as the 2 shifting in the carbon oxygen bonds that happened in the previous step. I didn't want to confuse you with so many shifts, so I didn't show it in the same step. I'm showing it in 2 different steps. In the previous step, I told you that the negative charge on this oxygen moved towards carbon, and then from here the double bond moved towards oxygen, right? But after this shifting happened, immediately C6H5 will shift towards this carbon atom because this carbon will have 4 bonds already. But I didn't show you in the same step because you might get confused. So I'm showing it in 2 different steps. But when you write it in your exam, it should be one single step. So now we'll see. Look at the 1,2 phenyl shift. 1,2 phenyl shift is this phenyl is moving from the second carbon atom to the first carbon atom. It can be either way. This can be second and this can be first, or this can be first and this can be second carbon atoms. Now this phenyl group is shifting to nullify the charge, and what you get is C6H5, CO minus. There is a positive charge because one of the double bonds has been shifted towards oxygen, that is the electrons forming that bond is going to oxygen. So carbon will get a positive charge. I forgot to mention this, so please don't get confused. There's a positive charge, so phenyl has to go towards this carbon to nullify the charge. Now carbon is attached to C6H5. And then you have C double bond O and OH will come this. Next step is the shift of hydrogen. Hydrogen will shift from this oxygen atom, that is, it will leave this oxygen atom and it will go towards this oxygen atom to nullify the negative charge. So H plus is shifting. So what will you get? You'll get C6H5, COH, C6H5, C double bond O and O minus. This is called as carboxylate ion. Carboxylate ion because it's a carboxylic acid group. It's losing one proton, so it will form an ion. That's called as carboxylate ion. Now we will move on to the final step. The final step is the acidification, as I already told you in the very beginning. Acidification is simply the addition of a proton. It will attach itself to O minus to finally neutralize the negative charge that is present. So you'll get C6H5, COH, C6H5, C double bond O and OH. This is your final product, which is benzilic acid. Discuss the last type of rearrangement reaction, which is benzidine rearrangement. It is an example of intramolecular rearrangement reaction where the migrating groups do not leave the parent molecule. Here, hydrazobenzene is your reactant. This is warmed with mineral acids to give you benzidine. Benzidine has a molecular formula 4,4-diamino diphenyl. Hydrazobenzene is a derivative of azobenzene. This will react with proton because it's happening in acidic medium to give you benzidine. Let's look at the mechanism for this reaction. First step in the mechanism is called protonation. We know that protonation is the basic addition of a proton. It's hydrazobenzene with two benzene rings and NH which are linked. Now it undergoes protonation plus H plus. This proton is going to attach itself to both the nitrogen atoms. So both the nitrogen atoms will be protonized. So I'm writing again the same formula but NH2 and the benzene ring. Now I'm going to put a positive charge on each of the nitrogen atoms. This is because nitrogen atom has one lone pair of electrons and that lone pair has been donated or has been used to form a bond with the proton. So it will be deficient of those lone pair of electrons, thereby acquiring a positive charge. This will be your first product. The first product formed due to protonation is highly unstable because of the positive charge present. Thus, there will be a charge transfer in order to nullify these positive charges. So, I'm going to shift the double bonds. This bond is shifted here, this here, this here, this and this. All these bonds are shifted just to make these two positive charges nullified. So, I'm going to write the product formed due to the shifting of bonds. Those two rings are as such. The only difference is here the bonds are shifting away, here the bonds are shifting towards. So this carbon will get a positive charge since the bond is moving away from it. This carbon, there's a hydrogen atom here, we should remember that. And this carbon is getting the electrons from this bond, so it will be negatively charged. And there's a hydrogen here. And since the bonds are shifting, this bond is present here and this bond is present here. This bond is shifting here, so I'm going to draw those bonds according to the way in which they are shifted, and nitrogens will be bonded by a double bond with this carbon atom because there's a bond going towards nitrogen. So there's nitrogen, NH2 plus, and then again there's a double bond here, NH2 plus, and there's a dotted line here. I'm drawing a dotted line to show you that this bond is neither broken nor completely formed. That's why I'm retaining the positive charge on nitrogen atom. We still don't know whether the bond is breaking or not because it's a two-step process. I didn't want to show completely in one single step. Now let's move on to the next step. In the next step, this bond will break completely. Since this bond is breaking completely, there will be a bond formed here because of the attraction between positive and negative charge. So this bond will start to form. So I'm drawing those two rings, and NH2 plus is there as well. NH2 plus, NH2 plus. This bond has broken and this bond has formed. You have a hydrogen here, another hydrogen here, and these two double bonds are present. Now this will be your third product and this will be your second product. All of these products which I am numbering as 1, 2, 3 in numerals are all intermediates. The final product is what you will be numbering with a Roman number. Now this third product is also highly unstable. Now I have to shift the bonds just to make this third product stable. How will I shift the bonds? I'll show you how to shift the bonds. This hydrogen atom will leave, giving its electrons. First, this hydrogen atom is going to leave. When it leaves, there will be an electron left by this hydrogen atom which will form a bond here. So the bonds will shift completely. This bond will shift, giving an electron, making NH2 plus as NH2 neutrally, making it neutral. And then this bond will shift here, giving its electrons. Hydrogen is leaving, so a bond is formed here. This bond will shift and this will shift. The final product will be like this. It will have the two benzene rings as such. Now NH2 plus has become just NH2 with a single bond. Here again NH2. They are not linked here. These two rings are attached here, and the bonds, because of the shifting, will change their positions like this. So this is the final atom, or the final product, which is called as benzidine. I told you benzidine is the final product because when you look at the first general reaction that I showed, you saw that hydrobenzene in the acidic medium is giving you benzidine. This is exactly what we got as a product from the mechanism. Only the benzene rings are attached, not the NH2s. But here nitrogens are attached and not the rings. So this is the rearrangement that has happened. Thank you all. I am done with today's video. I am done with all the 3 rearrangement reactions. Thank you for watching my video. I hope it helped you understand these concepts better. I'll come up with new videos explaining the other rearrangement reactions because there are quite a few rearrangement reactions that I have left out. I will be making another part of this video explaining them.